Hello students, my name is Sushant Garg and I'm going to teach you here one of the topics of thermodynamics, which is called polytropic process. Okay, so first of all, to start the polytropic process, we have to take a gas which is having a pressure P1, volume V1, temperature T1. Suppose something happens, like we have given the heat to the gas or work to the gas, something, we have made some changes in this gas. Due to this change, its state will change and its pressure will become P2, V2, or temperature will become T2. So something we have done here to change the state of the gas. We don't know what. So how its pressure and volume will be connected to the changed pressure and volume by the law of the polytropic process called PV to the power n is equal to constant. So what happens actually in polytropic process, we do not say whether the pressure is constant, we do not say whether volume is constant, we do not say the temperature is constant, we do not say whether the heat given or taken out is zero, we do not say whether the work done by the system or on the system is zero. So if we define these things where nothing is being given, what is happening, like pressure is constant or volume is constant or temperature is constant, yeah, heat transfer is constant, heat transfer is zero, or work done is zero, nothing is given, then it is called a polytropic process. Anything can happen in polytropic process to reach the state of pressure P1, volume V1, temperature T1 to pressure P2, volume V2, temperature T2. So PV to the power n is equal to constant is the mathematical expression which governs your polytropic process, where n is called polytropic index. So what this polytropic index will do here, it connects P1 V1 pressure to P2 V2 pressure. Like if the pressure and volume to the power n multiplication will remain constant, it will remain constant of P1 V1 also and for P2 V2 also. So if we have to connect these two, we can connect like this, that's P1 V1 to the power n, P2 V2 to the power n, and we can find anything which we like. So this is the first important thing we can draw out from your polytropic process. Next is, we know the ideal gas equation. If we take this gas as ideal, then we have PV equal to nRT. Now putting PV equal to using PV equal to nRT, we can find the relation between V and T also. So putting the value of P, let us say PV equal to n, C say Vn to the power, or you can say we want to put the value of P, so P is equal to C to the power C by V to the power n, C to the power V to the C by V to the power n, V nRT. So this will give us V 1 minus n and RT. Now what we'll do here is, we can write it as C by nR is equal to T by V 1 minus n, and we can take V up by using this mathematical operation. What it will do, it will make minus 1 minus 1 to n minus 1. So we can write it as n minus 1. So C by nR, in C is a constant, nR is also a constant for a particular gas. We are not changing the number of moles, whatever we are doing, but we are not changing the number of moles. We are giving heat or taking out heat, we are giving work or taking out work from the gas, but we are not changing the number of moles. So constant upon constant will give you a constant itself. So TV n to the power minus 1, this is one of the second relation, we can use it in our polytropic process. So first is your PV to the power n is the constant, second is TV n minus 1 is also constant. Similarly for pressure and temperature, we can find out by using any of this, or PV is equal to nRT we can use. In PV equal to nRT, we have to find the relation between P and T. What we do, P and T. So what we do, we put K, like we can use this. We can use Vn to the power K by P. What happens in Vn to the power K by P? Just write it out like this. So take power of n on both sides. Now what happens next? We have to give power to their individual variables. nRT will also get the n power, T will also get the n power. Now in place of V to the power n, we can write it as K by P. We can write it as K by P, and V to the power n value we have written nR to the power n, T to the power n. So what we will get, P to the power n we have also had. So what we will get here is Pn by P, K, nR to the power n, T to the power n. So Pn minus 1 we will get K nRn T to the power n. So after getting this, we have to arrange it in the form of T to the power n. We have to take constant on one side, 2 to the power n by Pn minus 1. So K by n to nR to the power n will give you another constant. Let us say K dash, and this will be written as Tn P minus n minus 1. So K dash T to the power n, what we will get here, 1 minus n. Why have brought it like this? Why have we have not brought Tn in the denominator of P to the power n minus 1? Because in the standard form in the textbook it has written like this. So you must follow this strategy or this notation, otherwise you may do wrong, or you may do in such a way in examination which you may do in such a way in the examination that the answer you will get we may not match the options. So first we got PV to the power n, K, or we can say C constant we took, and TV gamma n minus 1, that has given us K, and K dash is equal to T to the power n P1 minus n. So these three are the polytropic relations between pressure, volume and temperature, which we can use to find out the changed pressure, volume, temperature if the polytropic index is given. Now in the next part we must find out the work done by the gas during polytropic process. So let us say the small work done by the gas is equal to P dV to the integration of P dV. Now we know PV to the power n is a constant. We can write it as P equal to C by V to the power n, dW is equal to C by V to the power n dV. Now if we do the integration on both the sides, what we'll get, C should be taken out, V to the power n dV. Now the integration of 1 by V to the power n will give us, first of all we can write like this, to the 1 by V to the power n. Now next step will be the integration of V to the power minus n plus 1 by n plus 1. We can write it like this. Now here minus sign is also present. So next will be C V1 minus n by 1 minus n. From PV to the power n equal to C, we can replace C with PV to the power n, PV to the power n, V1 minus n, sorry, divided by 1 minus n. What happens next? Pressure, and if we multiply V into V to the power n to V to the power 1 minus n, we have to add the powers, through which we will get PV by 1 minus n. This is the polytropic work which we will get. Now putting the limits here, we have to put the limits also if we have done the integration, like from pressure P1 V1 and volume V1 to pressure P2 V2 we have gone. So delta W will give us PV1 minus n, pressure and volume. Pressure and volume we have to put both the values, upper limit minus lower limit upon 1 minus n. In the standard form in which the books have written, we can write it like minus of P1 V1 minus P2 V2 upon 1 minus n. We can take the minus in the minus common in the denominator also, so it will come out as n minus 1. Minus minus will get cancelled. So this is the polytropic work, which is the formula which we can use in adiabatic indexes also. Interesting thing which we can take out is here is the value of n. In polytropic process, the value of n can be from 0 to infinity. Okay, so if we take n equal to 0, we will get which process? From p v to the power n equal to c. If we put the n value 0, v to the power 0 c, p will get constant. If n equal to 0 is used, we will get isobaric process in which the pressure is constant. And if we take n equal to 1, let us see what will happen. Pv to the power n equal to c, we will get Pv equal to c, which is the representation of isothermal process. So n equal to 1 will be used, we will get the isothermal process. If we use n equal to infinity, what will happen there? Pv to the power n equal to c, we have to put n equal to infinity, so we may not get any result from this. Let us use Tv n minus 1 is equal to c, whether we will get anything or not. So this we have to see. If we are using Tv n minus 1 equal to c, what we have to do? Take this form, then we can take power on both sides like this. We can take power on both sides like this. So what will happen? This and this will get cancelled out. We will get this, and LHS will get V. We have to give power to both T and it. So this form will get, put n equal to infinity. What we'll get? C1 by infinity minus 1, T1 by infinity minus 1. Infinity minus 1 will get infinity. So in the denominator we also get 1 by infinity. 1 by infinity will get 0. T1 by infinity will get 0. C to the power 0, T to the power gave 0. Both will give us 1. 1 by 1 is 1, which is a constant. So if we put n equal to infinity, we will get volume constant process, that is isochoric. If we are using n equal to gamma, we will get adiabatic process. So anything can happen in polytropic process. There is no certain boundaries that pressure should be constant or volume should be constant or temperature should be constant or heat transfer must not occur. So anything can happen in polytropic process, and the polytropic index can take value from n equal to 0 to n equal to infinity. There are specific cases in polytropic process which will give us specific processes. Now let us find out the specific heat during polytropic process. Let us give us the name it as, just we want to name it as, so we just name it as C. So from first law of thermodynamics we know delta Q is equal to delta U plus delta W. Delta Q we can write with the help of polytropic process. Let us say the number of moles we are using here is N. So NC delta T is the heat transfer of the heat transfer from the gas or from the gas or into the gas. So delta U can be written as NCV delta T, and delta W can be written as P1 V1 minus P2 V2 upon N minus 1. So next what we can do here is we can write it as NC delta T, NCV delta T plus P1 V1 can be written as nRT1 and P2 V2 can be written as nRT2 by n minus 1. So what should be the next value? Divide the whole term by n. So from here n will get L will be divided from here, n will be divided CV delta t, we are getting plus from here also n will get divided. So me not need to write it here, n minus 1. So next step should be we can write t1 minus t2 as minus of delta t. Okay, because delta t is t2 minus t1, so minus of delta t will be t1 minus t2. C delta t is equal to cv delta t minus r delta t and minus 1. So delta t will get divided from this equation, c equal to cv minus r by n minus 1. This is the specific heat during polytropic process we will get. So what are the results we have got? We got Tv n minus 1 and equal to constant. We got Pvn from where all the things were started, and the next one is which I almost every time forgot, p to the power t to the power n, p1 minus n is a constant. So these three will work done. P1 V1 minus P2 V2 by n minus 1. We can write it as nRT2 minus nRT1 minus nRT2 by n minus 1. Specific heat CV minus R by n minus 1. Or if we take out minus from here and make it as plus, we can write it as C equal to CV plus R by 1 minus N. So these are the forms of specific heats, and this is all the mathematical operation used in polytropic process. Hope you enjoyed the video. Please post another video on another topic sooner. Thank you students.